Morning, everyone. My name is John Allen. I'm a coastal geomorphologist with the Oregon Department of Geology and Mineral Industries, and so I work for the state of Oregon. I took over the tsunami program from my predecessor, George Priest, who has a long history, having reformulated much of the initial tsunami work in the state of Oregon. Was very involved in collaborations with Washington State as part of early modeling on Cascadia, leading to formations of regulatory lines and things like that. So I'm going to just speak to a little bit of history about the tsunami program. I wanted to then turn it over to Jay. Jay in particular is going to delve into the more recent work that's been going on with respect to developing updated logic trees for Cascadia. Because really that's the sort of nexus where we've reached. We've been using deterministic models in the past, which have worked well. But what we're learning is that obviously there's a lot more uncertainty in many of the different parameters. And so the PTHA process provides us with a mechanism to better understand and constrain a lot of those uncertainties by running many more models. And so we can use those data then to update other types of products like the ASC Tsunami Design Zone, or in some cases, potentially even using PTHA products for evacuation planning and so on. So I'm just going to give a little bit of history behind this process. But of course, all of this is leading up to preparation towards the next megathrust earthquake that we're all so concerned about in the Pacific Northwest. So, a little bit about my agency. So, and what you can see on this slide here is reflective across all NTHMP states and territories. So while I'm talking about PGAMI here and Oregon Emergency Management, Althea is on the back there, this really applies to all states and territories that are members of the NTHMP program. So all of us have both a science role as well as an education outreach role. And that all comes together through the National Tsunami Hazard Mitigation Program that Karina will talk about later on. We all focus on developing products. These can range from modeling type products that are used to develop maps, doing risk assessments for looking at the who, what, where in inundation zones and fatalities. We do extensive evacuation modeling. We support communities with developing and installing signage along our coastal margins to encourage people to know where to go in that event. We also facilitate discussions through our own Tsunami Advisory Council. And the importance of that is that we work with the communities to think about changes in products. We use that group to present products. And if there are needed changes to maps, this is the group that actually reviews those and makes decisions. And that process was really integral in the early 1990s when my predecessor, Rob Witter, was running the program and was developing the sort of second generation evacuation maps for Oregon. They worked with every community to define what the inundation zone should be. So that's a really key part of that whole process. We participate with the ASC Tsunami Loads Committee. And then obviously, Althea in particular, but I can be a science rep as well in the event of an earthquake, be it distant or local, in terms of providing guidance and things like that. So a little bit of history. So the first tsunami maps developed in Oregon was in 1985 by George Priest, using very simple techniques to map the entire coastline. Those maps were then adopted into a regulatory line. It was the first regulatory line in the nation, but obviously applicable only to Oregon. And the goal of that regulatory line was to basically mitigate construction of critical facilities in the inundation zone. So schools, hospitals, things like that. 1996, NTHMP was formed and really came out of the initial work that George and George Crawford from Washington State and others were doing in terms of that initial mapping in the Pacific Northwest. And the goals there, of course, was to do evacuation modeling, a lot of outreach, and then develop a warning system that we have today. From 1997 to early 2000, we were developing detailed evacuation maps from tsunami modeling for a number of communities. 2004, we had the Andaman Ocean great earthquake, 200,000 people killed. And really that instigated a substantial influx of funding into the NTHMP and then ultimately the states and territories that allowed many of us to actually begin to accelerate the tsunami programs, respectively in our states and territories. And so in 2009, we initiated a pilot study at Cannon Beach. It was actually funded locally by the community. We were evaluating a variety of tsunami deposits that were dispersed up the Cola Creek there, and then using tsunami models to validate the inundation models and see how they matched. And so those initial runs focused on 15 scenarios. A similar work started in Bandon that eventually led to the adoption of the state's existing maps, which consist of 5 deterministic sources to t-shirt sizes, small to XXL. And within there, we modeled both a shallow buried, and then a mega splay type rupture system. We also modeled 2 distant scenarios, the Alaska 64 and a maximum considered Alaskan event. And as a result of those pilot studies, the Tsunami Advisory Council then adopted a 2-zone map for the state of Oregon. So we have both a maximum considered distant evacuation zone, a local zone, and then we've got high ground. So 2-zone maps covering those two elements. Another key aspect that I wanted to point out is that in 2011, actually it was beginning 2011, 2012, NTHMP decided through recommendations from a national advisory committee that we needed to start benchmarking our numerical models and make sure that those models are actually meeting minimum requirements for certain analytical, lab-based and even field-based type studies. And that was published through a report and then eventually by Juan Haralo in 2015. And those benchmarking tests are still out there for people who want to actually validate their models. And I'll come back to that maybe a little bit later on. 2013, we produced our 2nd generation maps. We did another benchmarking workshop looking at maritime tsunami generated currents in 2016. Pat Lynette led that effort. 2017, the American Society of Civil Engineers published their 7-16 tsunami loads chapter and the tsunami design zone. And that had pretty significant impacts along both Oregon and Washington coast. In 2020, Oregon reversed through House Bill 3305. They repealed their 375 line. And so for a brief period there, they had no regulatory limitations on construction of facilities in inundation zones. So it's kind of a wild west for 1 year. 2605 passed in 2021, and that basically adopted the American Society of Civil Engineers product. But then recognized that as future iterations come along, they could replace that, which is where we're heading towards today. But our building codes adopted it, but then said, well, okay, you communities, you can make the decision. It's up to you whether you want to enforce them or not. So it was kind of a bit of a cop-out type approach. And then 2023, Dan and Pat Lynette read a debris modeling workshop, again for NTHMP models. Shortly after that, Jim Kirby and Stefan Grilli ran a sediment transport benchmarking workshop. And then here we are in 2024. So the main point I wanted to highlight here is that the strong sort of association between states and territories developing their products and doing all this mapping and modeling, but actually being guided by benchmark testing and guidance documents that are developed through the national program. And that's really quite important. So all of us, every state territory who is funded to develop maps has to actually meet minimum sort of standards when we develop these products. And that's really important going forward. And it's actually an area that we need to revisit. I mean, this original benchmarking was done in 2011. The models that are there are they're good, but certainly the real world examples are pretty coarse. And there are much better real world examples out there. And so one of my recommendations going forward to the NTHMP is that we actually look to a future benchmarking workshop in the next few years to update some of these things. I'm running out of time, so very quickly. So this is a comparison of our t-shirt sizes from small all the way up to XXL. On the right-hand side, you've got elevation in the mean high water there, taken at the 100-meter bathy contour. And then in gray, you can sort of barely see it, is the 1,000-year PTHA from 2016. In black is the 2475 year overlaid on all our scenarios. And then the main point to note is that the 1,000-year, we had speculated it probably would track closer to our median, but it turns out it's more conservative. And then our would be close to the 2475, but it isn't. And I guess, you know, when you think about it, it's not surprising because PTHA includes so much more uncertainty in there that you would expect it to be a little more conservative. But this caused angst within the states of Oregon and Washington. And so really leads towards some of the work that's going on now. There are other concerns. So this is an example from Gold Beach on the very southern Oregon coast. It's closest to the subduction zone. The wave arrives in about 10 minutes. In gold is the L1. You can see the dashed line here, which is the 2475 year. So it's showing it's actually west of what we think where the 2475 year should be. We think it should be further east of that where it is now. There's a school right there, right at the junction that's in the inundation zone. And so this highlights one of the concerns, plus you can see all the coarse nature of the grid modeling that was done. They modeled at 60-meter grids, which is really insufficient. Another example, this is up by Seaside. You can see L there, but in this case here, the 2475 is well east of even our XXL scenario in some cases. So there are these differences along coast that are probably a function of differences in modeling physics, probably differences in bathymetry for sure, and various other factors. So we need to resolve these going forward, which brings us to where we are today. So why are we doing PTHA now? Well, there's been lots of improvements. We've got better bathymetric models now developed by the National Center for Environmental Information for both Oregon and Washington. We have refinements to the Cascadia sources that Jay's going to touch on. And then we've got, you know, these original models that were done on using very coarse grids. So where we're at, we funded Callan's work to develop new deformation models that could feed into the updated logic tree for Cascadia. And that was courtesy of NTH&P. And then we're actually just starting the tsunami modeling now. And then looking to the future, a goal would be to eventually develop much better PTHA curves rather than being reliant on offshore sites. We would actually develop these hazard curves on land. So this is the original 2016 logic tree that was used. There were about 700 sources there published by Honky Theo, consisting of both partial ruptures and then full margin ruptures. You can see the various elements there that Jay will go into. This is where we got to at the end of last year as a result of the Cascadia Power Center working group. It's now consistent of, again, full and partial rupture scenarios within logic tree. There's a Bugani branch which emulates some of the aspects of the original work that George and Robert and others developed. But really the main effort over the last 12 months has been to fill out the rest of the logic tree based on a lot of new information through Harold's work and his students, as well as Kavots and others and things like that. So this is kind of where we're at today. This is an example of where the ASC new lines, new offshore amplitudes have got to. 2016 is in dash there. The solid black line is the new for a single point, and then you can see Alaska sources out here. What we're seeing right now is that there's been a slight shift towards a little bit coarser, a little higher amplitudes for this particular points for a 2475 year, but our larger scenarios are actually being reduced now as a result of these updated results. And I'll stop there and let Jay go into the next part.
That is different slides.
All right. On the same way.
That's not the same slide that you're using.
That's not my presentation. So I have a separate presentation.
Okay.
Well, thanks for having me here today. I'll be reviewing the updated PTHA for U.S. states and territories using the Cascadia component. as an example. And I like to use Alan Nelson's method of reading their slides. So that's why I have my laptop here. And of course, if it's not fun, it's not worth doing. So we have a little animated GIF.
Is that the correct one?
I try to bring in new animated GIFs. So if you have any good animated GIFs, send them to me and I'll use them. That's not it. I know you're doing all your best. There we go. All right, and for some reason it's not working. There's Cookie Monster.
Okay,
Okay,
1 second, it's still loading.
still loading. There we go.
Sorry.
There we go. And I gave credit to where I got it, always from Reddit. All right, I'm Jay Patton, working at California Geological Survey. I've listed the members of the California Tsunami Program. And okay, awesome. And so today I present a summary of the results for the May 2022 U.S. Geological Survey Tsunami Sources Powell Center Working Group, Cascadia, PTHA. My co-authors are listed here, and the PIs for that Powell Center group are in asterisk. Next slide, please. Oh, that's me. I can do that. Yes, I might be able to do that. Here we go. All right. So in May 2022, live and remote participants in the photo gathered, excuse me, to discuss peer-reviewed literature that has implications for tsunamigenesis along Cascadia. The presentations and discussion were used to develop a logic tree. Will be used in an input for PTHA. And one major goal is to keep the PTHA consistent with the USGS National Seismic Hazard Map update. So I'm going to skip a lot of the detail on some of these slides because people have covered this material. PTHA is a process used to develop a framework to inform tsunami modeling and hazards analyses. Process uses a logic tree approach to collate the entire suite possible and probable tsunamigenic behavior for tsunami sources relevant to the area of interest. And logic tree is a way to calculate the relative likelihood for each of those all possible scenarios for a given phenomenon. And so this is an example logic tree from Dogami. And basically each of these parameters has a certain amount of different variability. And so each of these, so this is for earthquake size. And so each of these parameters is given a weight based on subject matter experts' estimates. And these all vertically have to add up to 1. So if you add up those numbers on earthquake size, it all adds up to 1. And then each branch has a scenario weight. So in this example of a medium-sized earthquake with shallow buried rupture, it has an 11% probability. And so these logic tree weights are used to constrain fault slip and tsunami source modeling, and the outputs from these tsunami models result in a suite of offshore tsunami heights representing the chance for tsunami sizes of a given annual probability of exceedance. In the plot on the left, each blue line represents an actualization of a suite of logic tree scenario tsunami models, a percent chance for tsunami size with an annual probability of exceedance in the vertical axis. So this plot represents thousands of tsunami models. And then using this entire suite of results, we can calculate the quantiles that are shown on the right, the bracket, the range of probabilities. And so the plot on the right, these are both tsunami hazard curves, but the plot on the right shows those quantiles. And so as an output of the Cascadia Powell Center workshop, Dogami and John Allen funded some work for Callan Wong and Matt Sipus to construct an updated Cascadia megathrust surface deformation model that's being used for the initial conditions for the tsunami wave simulations. And lots of the updated information came from KC21 data and interpretations that we've already seen. And so this is a slide I don't need to spend a lot of time on. These are the KC21 data track lines. And in the center, we can see in color the picks for the top of the crust. And the next slide. And so Matt took the picks provided by Suzanne and mapped both the top of the crust and the décollement, which is in different positions in some places, as Harold mentioned. Offshore Washington, top of the crust and the décollement are co-located, and then offshore Oregon, the top of the crust and the décollement are no longer collated. The décollement is in the middle of that sedimentary section. And I'm gonna just skip that slide to save time. Oh, you know, I have dyslexia, and I basically prepared a 75-minute talk, but it was because it was a 25-minute talk and a 2 looks a lot like a 7. That's not really true, but I prepared a 25-minute talk, and also blaming dyslexia for not recognizing that I was actually sharing the 25 minutes with Harold. So that's why I'm skipping through a lot of these slides. And then in Southern Cascadia, where due to potential permitting problems, KC21 didn't collect new data. And so Ann Trehu provided picks for the up-dip portion of the megathrust geometry. And I forgot to mention that Bostock and his students provided down-dip constraints for the slab geometry. All right, let me catch up here. So here, here you can clearly see the Cascadia logic tree, but let's look into this in a little bit more detail. So, so Cascadia has 2 main branches that you saw on the other slide, and the whole margin branch, and then partial, branches, partial margin branches. So the whole margin branch breaks into, as John mentioned, the Duogami and the USGS branches. The Duogami branch uses local geology and paleoseismic studies where rupture scenarios are based on inter-event time, referred to the t-shirt sizes. And the USGS branch is based on the Western US National Seismic Hazard Model. They use global scaling relations, possibly not relevant to Cascadia, but that's what we have to calculate earthquake magnitude and rupture characteristics and paleoseismology to constrain earthquake rate models. And so just a quick review of the t-shirt sizes. So the Duogami devised, Brian Atwater actually came up with the idea to assign t-shirt sizes to the grouping of earthquake events based on inter-event time. And so the basis for this t-shirt sizes is scientific, but people think, oh, t-shirt sizes, whatever. So, but it's based on the inter-event time of those earthquakes. And the logic tree in the upper right, as we already saw, shows the weights of those branches, and the histogram in the lower right shows the distribution of those t-shirt sized full margin paleo earthquakes. Okay, next slide. So the USGS branch splays into single rupture and clustered M8. Now, clustered M8 are not single ruptures, but this is where the USGS has it in their logic tree, so we're adopting that. And let's see, so the single ruptures use the scaling relations, but for a single rupture, so Strasser, those are the scaling relations that the USGS uses. And then the clustered M8 use the same scaling relations, but distributed across 2, 3, or 4, or 5 events. And I have some maps, hopefully we'll get to. So as John mentioned, as John mentioned, the remainder of the branches in the logic tree are, they are applied to all of the previous branches. But this was the focus of the Powell Center workshop where we really, spent most of our time. And these all relate to the geometry of the potential fault rupture. So these branches, so there's, if we, go from left to right, now, logic trees, it doesn't matter the order that you put these in, mathematically or probabilistically, but it does matter to help you understand the processes, handling processes. So the first branch we see is seaward vergence versus landward vergence, and we're going to look into all this in a little bit more detail. And then regions of the margin were subdivided based on fault vergence. The up-dip rupture characteristics, whether they're trench breaking, buried slip, or splay fault slip. The splay rupture branch was broken into two fault options, splay fault B and splay fault D. And a reminder that the work that Madeline and others have done was happening while we were developing this. And so we weren't, it wasn't really possible to completely incorporate all of their excellent results. And so lots of the results that have been developed and are still developing will be incorporated into the next generation PTHA. But so we were really just lucky to be able to get what we got. So there are things that are in the logic tree that we now know are less correct than they could have been. But that's how we advance things. The buried branch splays into deep or shallow buried rupture, and splay B has a shallow slip option. The trench breaking branch is tapered to the trench at 50 or 100%, and I have a plot that shows what that means. And the shape of the slip in the along dip direction, the down dip and up dip direction, has different branches depending upon the type of up dip rupture. So branches can include skewness, so up skewed slip, symmetric, or down skewed slip. And the down dip termination of slip is constrained by the three criteria as implemented in USGS NSHM. And the slip distribution is broken into two branches, 3 asperities, north, central, south, and 5 asperities. And I have some maps that we'll quickly look through in a moment. And so finally, the last slide on the logic tree is the partial margin branch is broken into 2 branches, segmented and floating. So floating being random slip patches. The segmented branch is based on paleoseismic scenario boundaries. We're trying not to call them segment boundaries, but for, so we'll have to change the logic tree, call those scenarios A, B, C, C prime, D, and F. The floating branch is broken into southern versus whole. I have some maps to show that. And then we have a B value variability, B equals 1, B equals 0, and subduction zones have a full range from 0 to 1, and we don't really know what Cascadia is. And so those have an equal weight, 0.5, 50%, each of those B values. And then the earthquake rate branches are based on recurrence rates from different publications, like the recent paper by Nelson et al. Is constrains 2 of those rates. And the partial branch then includes the subsidiary branches that we looked at in the last slide. So here's a slide that shows us the along strike variation in slip. And so this illustration shows we have the full margin ruptures, the A and the A plus the explorer plate, and then those paleoseismic scenario ruptures based on paleoseismology. And then the next slide shows the along dip variation in slip. And the down dip, as I mentioned, the down dip limit of slip is based on the USGS National Seismic Hazard Model. And then the up dip variation in slip, we have the trench breaking, the non-trench breaking, the buried dip in buried rupture in the gray, and then the splay fault rupture in orange and in blue. So let's look at the slip in the down dip direction. And so this, when I mention, up skew in red, down skew in blue, or symmetric, this is sort of showing us what that means. The splay rupture follows the symmetric curve, but then it terminates at the location of the splay fault. And then when I talked about tapering to 50% or 100%, this is sort of what the up dip slip would look like for those 2 branches. We've seen a lot of this before, so this is basically just about the splay fault. And these are the two splay faults that we use in the logic tree, splay B or splay D. Splay B in blue is the geometry that we included because the states have been using this as part of their tsunami modeling for a long time. And so something I learned from Art Frankel is that NACHM is driven by the engineers. And so you can't, if the PTHA or PTHA changes too much from version to version, the engineers won't adopt it. And we want to ensure that the engineers adopt the science that we're generating. And so this is part of the reason why we wanted to include the L1 is because we didn't want the hazard to change significantly. And so, anyhow, that's something that people think that the geologists drive the seismic hazards and tsunami hazard process, but it's really the engineers. And there's nothing wrong with that. Right, because we all work together. And so fault versions, Watt and Brothers remind us that landward vergent regions may be more favorable to strain accumulation and more prone to trench breaking rupture. So that's why it's important. This is just a slide showing in red, we can see the fault vergence, how it varies along strike. Sometimes it's landward vergent, sometimes a seaward vergent, sometimes there's mixed vergence. And so this is showing the results of Janet Watt and Chris Goldfinger's interpretations of fault vergence. And then this is Shio Shuohan's interpretation using the KC21 data. And then this is the map that we developed where we, where there's any evidence for seaward vergent thrust faulting in yellow, a single frontal thrust is used. And where there is no such evidence in green, we use a highly upskewed buried slip. And so now I'm just going to show one map to describe what the next few slides have. Whoops, yeah, okay. And so the next series of slides, and we're only going to spend time on this one slide here, have maps in the upper left show the slip along the fault for different logic tree branches. And in the bottom left are the maps that show the coseismic vertical land motion, the deformation from the maps above. And then the upper right corner are these down dip profiles of, so this is the vertical land motion, the uplift. This is the slip for those at these different profiles for these two examples. And so this is the example for hole margin. You will see that, this is, let's see, so this is the deep rupture and this is the shallow buried rupture. So you can see the difference. And then I'll just quickly go through these. This is an example showing up skew, symmetric, and down skew. And so we can look at the up skew versus the down skew and the symmetric. And there's some differences there, just believe me. And then these are examples showing the differences in the down dip limit of rupture. And see, this is a deeper rupture here, lower down dip extent. These are examples that include the two splay faults. So here's, let's see, this is splay fault. Let's see, I think this is splay fault D and this is splay fault B, that L1. And then examples for margin trench breaching with the, and then these are examples showing the Dogami hole margin asperity split into northern, central, and southern asperities. These are examples for the hole margin asperity models. And then this is the map showing the clustered models from the NACHM. And these are those different 5-level clustered ruptures along the margin. And then these are the areas that are the area of floating rupture boundaries. And these are the maps and for those floating rupture boundaries. Thank you very much. Yeah.
Question?
Who is moderating that one?
Yeah, I'm.
We're all caught up on time.
Okay. Yeah. Very good. So we have time for questions, so anyone wants to ask? Jay or John? Yeah.
Hi, so I was curious, so it looks like the slip models for splay fault geometries suggest that all of the slip would be taken up on the splay fault if the splay fault ruptures. Is that correct, or is there some partitioning between megathrust and splay?
There is slip on both the megathrust and the splay fault. If, hopefully these presentations will be available to everyone after the thing. And so if you go through the slides in the profile that I showed with the upslip, the down dip profiles, you'll see that the display fault one had that they had the symmetric curve, but it terminated at the splay fault. So the splay fault would have a slope distribution also, but the plot just has the megathrust.
Yeah, but I guess I meant up dip, like past the splay fault. Is there
Right.
any slip on the megathrust past the splay fault?
Thanks for the clarification. So no, there is no slip on the megathrust beyond up dip of the splay fault. Great question.
Okay. Stand here.
I just want to ask if you are considering to add the effects of sea level rising due to climate changes for future maps. And I
That's
have
a
two
great-
comments on the follow-up of your of your answer.
Okay, I'll yell or thanks. So currently, sea level rise is not incorporated into the ASC tsunami design zone. And the reason why that I understand is because so the design zone is based on the length of an expected structure, which is usually about 50 years, maybe 100 years. And so the sea level rise over that period of time, at least for 50 years, it probably doesn't affect the structure in that period of time. And then also the tsunami design zone is updated every 7 years, I believe, 7 or 6 years.
So it is included.
Oh, okay.
There is an option there to incorporate the sea level rise component when you are designing for a vertical evacuation structure building. But not correct, yeah. But it's not built into the PTHA process. That's independent.
So I have an observation about that, because it's good what you are saying in terms of we're updating every 6 years the hazard. But anyway, we are building things that eventually will need to last 30 or 50 years. And in 50 years, it start to become actually significant.
Yeah.
Actually, I have a paper in review actually showing them. Well, the picture you saw yesterday, we're talking about food.
And it actually influences the innovation and the energy.
Yeah.
Even during the lifespan of 50 or 100 years. If you consider, we did that study for Northeast Atlantic, and during for the lifespan of 50 or 100 years, we consider about 1 meter of sea level rising, and it affected about 20 to 25% of the inundated area, and the waves were arriving in completely different energetic level.
Yeah, and there is a matter of height.
To
and
be
also
clear, I
height.
completely agree with that. I'm just saying, like, the party line, this reason, yeah.
Done. Have the microphone.
On the whole sea level rise, there's a new chapter that's going in called future conditions, where the IPC and all that kind of stuff is being considered, so that's for 28, 720. So there's a whole new section on the climate change, and it's going out to 100 years. My question, John, excellent presentation. There's a lot of emphasis on Cascadia, because that's the really big one, that's kind of for extreme design, but we talked to the Port of Newport. They were focused on the far field, the 100-year, because they said that's something they can afford to work on. When the really big one hits, they're not too worried about being back in distance right away. So my question is, how much of the PTHA is going to include these far field events? So we have
So it does.
description. It does. It'll have both.
It'll have both, yeah,
Okay.
yeah, and I mean, I very briefly touched on it in that hazard curve that I showed. So that hazard curve showed the full PTHA for 2016 and 2024 that incorporates all distant sources, but then you also saw the disaggregated sources separate from that. And so you can clearly see that in the case of Cascadia, the Alaska sources are particularly significant for Oregon and Washington. So it is in there.
But you need a logic tree as complex for Alaska as you have for Cascadia.
And it's being developed.
Okay.
Yeah.
But then we need one for Japan and the illusions as
that's
well.
right.
They're all,
And it's being
they're all
developed.
part of it. They're all part of it. I mentioned that this Cascadia was just the example for Cascadia. But we held week-long workshops for we held a week-long workshop for Alaska. We held a week-long workshop for Cascadia. We held a week-long workshop for Eastern US and Caribbean, and we held a week-long workshop for Pacific sources, non-Alaska, non-Cascadia. And we held a week-long workshop for coastal faults. And we plan on a week-long workshop this coming year for landslide. And we're talking about holding a week-long workshop for the development of the future of PTHA in the US. Hopefully, we just need to get some funding for that.
Volcanic tsunami, no?
Yeah,
Like-
well, actually, that was part of the Pacific sources. We had a volcanic session.
So just as a follow-up, Diego, I didn't really touch on it, but maybe you saw it, but in the original 2016 logic tree, the number of sources, the number of source models that went into that logic tree was like 700. The new one is 32,000. And for Alaska, it's like 42,000 sources, unique sources now. So these things have grown exponentially. And it's, you know, to your comments yesterday, it's quite a challenge when you're trying to model a number of these.
Oh, yeah.
I also have a question regarding the logic trees. And yesterday during the poster session, Diego had the comment, oh, why are so many recent earthquakes multifold? And we know that like the source dimension scaling relations for multifold earthquakes are maybe a bit elusive. So do we have to take that into consideration in the logic tree?
There was considerable debate about whether or not to use global scaling relations in Cascadia, because some people think that they just don't really apply, but they were part of the NSHM, so we're sort of, you know, don't record the, oh wait, I'm recording this. We're sort of stuck with using those global scaling relations, but this is an opportunity to mention the difference between active research and PTHA. And so PTHA can only adopt things in the process once it's been vetted by science, in academia. And so, you know, a single paper, you know, may not be enough to get into PTHA, but once there have been, you know, a handful of papers on a subject, then people are ready to debate it and, you know, use their subject matter expertise to place a weight on that. So that, what you brought up will be important to, so academia, we really need to, you know, get more publish or perish, which I disagree with strongly. Is important to get those papers out and so that they can be adopted.
Yeah, just an observation with the scaling, but remember that those are log plots. And when you go to the big earthquakes and the big lengths and the big width, actually the error, you see the dispersion and yeah.
I was sorry, when in the construction of the logic trees, you mentioned that the weighting associated with each branch is given by an expert. Is there any fear of bias going into those weightings?
So.
So basically what we did, just a background on the process is that, what we did is we set up a poll and people would vote on those polls. And one of the questions is people self-selected their level of expertise. Now that wasn't actually used in this. But I'll remind, science is 100% subjective, right? So the interpretation of the results is 100% subjective, but people often think that science is objective. So there's always some bias, and that's going to come through in the subject matter expertise weightings.
Thank you. So the thing is that we are running out of time, but Mohammed, you can do a quick question. And then we jump into the presentation.
Yeah, do you have any plan for joint seismic and tsunami hazard assessment?
So that's something we've talked about, and there's a desire to head in that direction. And I think that's still an ongoing research question that this group and many others can contribute towards. So I think, in the short answer is yes. We'll see, as Jay indicated, these types of results need to be published eventually and then discussed broadly by the scientific community. I mean, that's one of the values of the process of the Power Center workshops was that, the number of individuals, number of scientists involved, both science and in the emergency management community involved in that process and making these decisions collectively. This has been a huge shift from where it was in, say, 2016, which is a much more limited group of people making decisions. So the short answer is we'll get there.
Okay, so now we got sorry for that. When we are doing that, only 10 minutes late. So now we will introduce Corinne. No, it was perfect. Yeah, we have time. This is the purpose of the meeting to discuss.
All right.
Thank you, Corinne.
Yeah, okay. So I was asked to talk about the NOAA Tsunami program and how we take science and put it into policy and apply science and decision-making, and specifically also about the National Tsunami Hazard Mitigation Program. And so I'm new to NOAA. I'm the new Tsunami Program Manager. I started in July. Previous to that, I was the Chief Hazard Geologist at the Washington State Geological Survey. And so I've been with the NTHMP in that role for many years prior to this. And so some of this is new to me, but I've been in this space for quite some time. So I'm going to take you on a tour of the universe, but really what I call this the universe. So this is a magical place full of science and decision making and policy, where we all come together. We're all part of this universe to take what we know and apply it. I'm going to zoom in and I'm going to teach you about the NOAA universe. A funny thing happens when you zoom into the NOAA universe. Org charts start appearing. It's pretty incredible, and I'm not sure exactly why. It's one of the great mysteries of science, but I'm going to take you on a tour of our org chart, because I think it's really important to understand how tsunami touches all aspects of NOAA. And how it works well together, and how sometimes it can also be a little bit siloed. And so NOAA sits under the U.S. Department of Commerce, and in the big NOAA, which is the second level on this org chart, the places where tsunami starts to creep up is in two places really. So one is NOAA has a science advisory board, which advises it on all different things. There are many different working groups under the science advisory board that make formal recommendations and reports that go to the NOAA administrator and then also to Congress. And NOAA is required to respond to those and ideally act on those recommendations. Under the science advisory board, there is a relatively new working group called the Tsunami Science and Technology Advisory Panel. And this panel was mandated by law in the Tsunami Warning Education and Research Act, and was first initiated in 2020. And several people in this room are members on that panel. And so the Tsunami Science and Advisory Panel, or the TSTAP, makes formal reports and recommendations to know about all things tsunami. How can it do better with the universe? And so the first report from the T-staff came out in 2021, and NOAA is actively responding to those recommendations. And reports to Congress happen every 4 years. And so if you have an idea or a recommendation, you can approach that group. Carrie Garrison Laney is one of the co-chairs of the T-staff right now. And so if you have an idea, feel free to reach out to Carrie. Another place where tsunami creeps up at this level is post-tsunami event response. And so many line offices in NOAA have some response capability after a tsunami happens, whether it's tide gauges or darts or field data collection or ocean services, that creeps in at this higher level of NOAA. Now I'm gonna take you down to the next level where a lot of the org chart starts to expand and we have lots more pieces of the pie. These are our planets, maybe, I don't know. And so a lot of what happens in this universe at NOAA happens under the National Weather Service, but also under the Ocean Service. This is where tides and currents and tide gauges are located. The people responsible for that coastal observing systems are all under Ocean Services. Under the National Weather Service branch, we have the NOAA headquarters, which is where I sit, where the NOAA Tsunami Program sits, where the National Tsunami Hazard Mitigation Program sits. And then you have regional offices that are located all around the region. And each of those regions have local weather forecast offices, which have some tsunami response if they're in a region which has a tsunami hazard. But then under the Pacific and the Alaska regions is where the two tsunami warning centers sit. So you have the Pacific Tsunami Warning Center in Hawaii and the National Tsunami Warning Center in Palmer, Alaska. I don't know what happened. I didn't touch anything. And then you also have the International Tsunami Information Center, or the ITIC, which is really important because it works all across the globe to understand best practices in tsunami outreach, preparedness, hazards, observations, detection, warning, forecasting. It coordinates with all of these groups all over the world and brings those best practices back to the United States and shares our best practices globally. And then you also have the National Data Buoy Center, which is in charge of deep ocean assessment and reporting of tsunamis. So those are the DART buoys that they're referred to. So that's how we detect tsunamis and incorporate those observations into forecasts. And then going over on this org chart, the satellites and information, that's where the National Centers for Environmental Information sits, NCEI. They are the entity that's responsible for creating these digital elevation models that we all use for tsunami hazard modeling and mapping. They also formally archive tsunami event information, and they host that. They have the global tsunami database, they have marigrams, they have a lot of really useful information for validating and understanding tsunamis. And so that's a great resource. And then under the research arm is where the Pacific Marine Environmental Lab sits, and they have the NOAA Center for Tsunami Research, or NCTR. And that's the group that is in charge of developing the forecast models, the MOST model, and working to provide the National Tsunami Warning Centers with their forecasting capability and emerging and increasing tsunami research and science. And so all of these groups work together in NOAA with all of you to incorporate best practices and then hopefully put it into practice. And so a couple of years ago, the National Weather Service got a new director, Ken Graham, and he came up through the ranks of the Weather Service. And when he took his job, he started an initiative, the PENS 10. What are 10 things that he can do to improve the National Weather Service? And one of the 10 goals that he is focusing on is the NOAA Tsunami Program. This is great because there's an emphasis on improving the tsunami program, breaking down silos, creating consistent backup capabilities for the tsunami warning centers. And so I'm going to talk to you about some of the activities that we're doing in NOAA as part of that effort, and then I'm going to jump in and talk to you a little bit more about the NTHMP. So one of the big projects we're working on right now is aligning the two tsunami warning centers. As I mentioned, they are both one is in Alaska, one is in Hawaii, and they're both under different regional offices, and they both have sort of come up independently. They have different forecast software, they have different systems in place, and a lot of their systems and technology are very outdated. And so in theory, they're backups of each other, and in practice, that's a lot more challenging than any of us would like. And so one of the goals of the KENS 10 initiative and one of the recommendations from T-Staff is to operationally align the two tsunami warning centers so that they can have full service backup capability of each other, and are unified under a single chain of command. And so that is a project that we are currently working on. And I'll talk a little bit more about that. Another, in the event of a tsunami, the authoritative source of information is the tsunami.gov website. That is the website, tsunami.gov. And that's where you find alert bulletins, areas that are in different warning levels, different forecast information. And for anyone, how many of you have visited this website? I'm curious. Guys, half the room. It's in dire need of an upgrade. It's, I think like many government agency websites, I could say, but it's seen its challenges and in events. It's been known to crash when too many people visit it, which is not a good thing. And so we are currently redesigning that website so it has improved functionality and resources. So that's a big undertaking. We're also conducting a social science study on alert terminology and hazard simplification. So across the National Weather Service, there's an effort to simplify hazard terminology and possibly remove the advisory level alert. So in a tsunami event before, alert terms are warning, watch, advisory, or information statement. And so many of you might not even know what that means, right? Which is higher, which is worse. And so there's an effort to try and simplify that terminology. But that comes with a lot of challenges for the local partners who have socialized this, who have it in their emergency response plans, who have actions based on it. And so you can't just take away a term without understanding how that would impact people and then providing resources. And so there's a study to understand how do people use this advisory level term and make recommendations for should it go away, and if so, should it be replaced with something else. I'm going to dive into the next two bullets on the following slides, but in an effort to align the warning centers, we're developing a common analytics system and then a better process for sending tsunami alert bulletins out. And that's called the ATOMS, which I'll get into next. And then all of this is only successful if people know what to do with this information, right? If people understand the hazard and can make informed decisions based on the information they are receiving. And so in NOAA speak, that is impact-based decision support services, or IDSS. And so this is really important to all of us. It's really important to NOAA. And so we're developing a vision and a plan for enhanced IDSS capabilities, both in an event. So, when a tsunami happens, but then also routine IDSS services so that people understand and can plan and prepare successfully. And then lastly, all of this is super important, but if the staff at the warning centers aren't aligned and trained and exercised and coordinated, then it's not going to be successful. So there's really an emphasis on staff, on the people that are involved in this effort as well. So a little bit about the common analytics system. It's really hard to talk about this all in the limited time I have, so I'm going to breeze through this, but if you have questions, come talk to me later. We are currently in process. The Pacific Marine Environmental Lab is funded to develop the common analytics system for the two tsunami warning centers. It is it's a comprehensive and consistent data ingest and processing of observational data, so seismic data, tide gauge data, DART data, to understand the tsunami and then forecast for it, and provide redundant tsunami warning center operations. So it's essentially the software that the tsunami warning centers need so that they can better analyze the data, process the data, and forecast the data in a timely manner, and that it's consistent between the two warning centers, which it is not currently. And then, so the Common Analytics System, the CAS, is in charge of taking that data, processing it. So this side of this figure here, taking the seismic data, taking the DART data, processing it, and then providing that information to the ATOMS system. So ATOMS stands for Automated Weather Information Processing Services, AWIPS. That's the weather system that all NOAA weather offices use to issue weather alerts. And then the tsunami operational messaging system is what ADAMS is. So we love acronyms in the government, right? Org charts and acronyms. And so ADAMS takes the information provided by the Common Analytics System and recommends tsunami forecast messages and alert areas based on that tsunami event information. And then the duty scientists at the warning centers take that information based on their subject matter expertise, their experience and historical information, and they are in charge of issuing the alerts. And so this is bringing all of the equipment and systems up to date and into the modern age. And so this is sort of a flow chart of how this works. I just explained it. I'm talking too much, so I'm not going to go into too much detail, but essentially take the data, process the data, output the data, and then share the data with people through this IDSS. But I think the most important, almost one of the most important pieces of this whole diagram is the bottom block here that says routine IDSS. And so all of this only works if people receive an alert and know what to do with it. And so the day-to-day outreach and education and services and educating people about what to do if they receive a warning, a watch advisory, what to do if they feel an earthquake, what is a tsunami, what is a tsunami hazard, that's the routine IDSS part, and that is so critical to all of this being successful. And so this is a slide that sort of, this is what we're working on and then where are we going? So these are three big projects or big things that NOAA is thinking about. So I kind of touched on the two on the right here. But on the left here, this really ties into what John and Jay just talked about and what we've been talking about. Currently at NOAA and with the National Tsunami Hazard Mitigation Program, most things are deterministic event-based, right? Like we have the earthquake magnitude and that's all we know when we're issuing a tsunami, our first tsunami alert bulletin. But other hazards that the National Weather Service deals with, like hurricanes, which is the example here, they have the benefit of time, but they also have the benefit of more data, and they're able to make probabilistic forecast models and ensemble models and share, you know, there's a 90% chance of rain today, and then we can make a decision based on that information, what to do. Similarly with hurricanes. And so I think what we would like to see going forward is probabilistic forecasting for tsunamis based on probabilistic hazard maps and models, but also better data and information in a real-time event. We're a long way from that. That's not what's being designed in the current versions of the Common Analytics System, but it's what we're thinking about for the future. How do we get there? And then also trying to incorporate probabilistic tsunami hazard analysis into our understanding of the hazard and who lives in these hazard zones, which is what we've all been talking about so far today. And then also this ties into how do we send this information and share it with the people. So this is an example of a hurricane forecast or probability map. Currently, tsunami bulletins are all text. It just says, a tsunami has been generated. It will arrive at this location at this time, and here is the amplitude. What does that really mean for someone who has never experienced a tsunami, who doesn't know about tsunamis? You know, I think everyone would like to see a map showing tsunami inundation or the expected impacts of that tsunami. What is it arriving at high tide or low tide? What are the currents, right? This is all information that we've been talking about and wanting, but the practice of how do we actually apply it and include that is quite challenging, but it's something that we need help and we need to start working on and focusing on. So those are some of the big things that we're hoping to get there in the next decade, let's say. And then again, impact-based decision support services, I can't stress this enough. What do partners and decision makers need? What are we providing that works? What else could we be doing better? And how do we get there? And then lastly, really the Tsunami Warning Center alignment is critical for both during an event, but also science and technology integration, updating our procedures and technology and our coordination with our partners, and training and exercises so that everyone knows what to expect in an event. Now I'm going to jump to a really important part of the NOAA Tsuniverse, which is the National Tsunami Hazard Mitigation Program. John did an awesome job highlighting how that this program really benefits an example from Oregon and some of the products and services that are created through this. But for those that maybe don't know so much about this program, the NTHMP is a NOAA-funded grant program. It is also written into the TWIRA, the Tsunami Warning Education and Research Act, as a program that is an interagency program. NOAA is the lead, but we coordinate with FEMA and USGS, and then states and territory partners that have a tsunami hazard. And so these are the states and territories that participate or that are members of the NTHMP. So it's 28 states and territories, all coastlines that have some tsunami hazard. And so these partners are eligible to receive NOAA grant funds through the NTHMP to generate products that I'm going to quickly go over on the next few slides. And so we recently updated our strategic plan. I encourage you all to check it out. It's really great. It dives into what do we want to do? How do we get there? And so I'm going to go over the 4 main priorities or themes of that strategic plan, just so you can get a sense for what is the NTHMP thinking about and doing. So the first theme is hazard and risk assessment. I'm not going to read all of this, but this is what we were talking about primarily at this meeting. Identifying the hazard, who's in the hazard zone, how do we evacuate from those areas, and supporting tools and communication of the hazard to the at-risk populations. And on the bottom are a couple of examples. I don't have space to include all of the wonderful examples from states and territories, but please go check out that site to see the maps, the products, the services. There's an evacuation map here from Dogami. Here's an analysis of the at-risk population and who those people are from California. And then an example of maritime hazards from a tsunami event. Next pillar is mitigation, or excuse me, education and preparedness. So this is education and outreach, going to communities and talking to them about the hazard. It's putting up signage, it's practicing evacuation routes or practicing exercises. How do you get to high ground? It's building tsunami ready communities. Tsunami ready is a recognition program that communities can be recognized as tsunami ready, meaning they have a plan to evacuate, they have a hazard mitigation plan, they've coordinated with FEMA, they know what to do, and then they can be recognized as a tsunami ready community. And then conducting exercises at the local level and planning for tsunami preparedness. Next pillar is mitigation and recovery. So this is developing plans and strategies for mitigation and recovery. There is not enough funding and it's not in our purview to fund mitigation activities. So we're not building vertical evacuation structures with NTHMP funding, but we're developing plans and guidance and analyses for how do we do that? What are the best practices for maritime mitigation? Where do vertical evacuation structures need to be? And what about supply caches and all sorts of great things for mitigation and recovery. And then the last one is alert, warning, and response. So working with the state and local partners and providing a venue for them to engage with and make formal recommendations to the tsunami warning centers for improvements that need to be made to the tsunami warning products, and support the hazard simplification project, ensuring that the forecast information that NOAA provides is reliable. Tsunami response is effective. So this is where post-tsunami response comes into play, also is in this theme. So after a tsunami, teams of scientists go out and collect that information so that that can be used in validation and benchmarking activities for models, and field data are collected. So I just have 2 more slides of some recent NTHMP activities that are really cool to see like what's new and how, I'm done. Okay, 1 minute. Okay. So signages, Guam has this really adorable, awesome commercial that they air on their local television for tsunami preparedness that was funded through the NTHMP. Maritime response strategy, social science studies of how their communities understand tsunami risk. And then probabilistic tsunami hazard mapping and modeling is funded under NTHMP. Alex is working on a project right now for understanding wave arrival. Everyone uses the term wave arrival differently. It does not mean the same thing to everyone. So when we say the wave is arriving in 2 minutes, does that mean the crest, the trough, the first sign over mean high water, the maximum? What does that really mean? Exposure, population, hazard simplification, social science, all of these are great projects. So 1 more slide. So if you want to get involved, we need you. We rely on you to share with us the best up-to-date science, help us learn about it and implement it and communicate. And also leveraging different funding sources, I think is something that we all are going to look for in the future. If you have a NASA grant or a NEHRP grant, can we combine those with the NTHMP grants to be more successful? So with that, I'm done. Thank you.
Okay, open the room for questions. How about, well, the thing is that we will start with the question related with this presentation, and then we will jump into roundtable. So let's focus on this presentation.
Marina, thank you for a very informative discussion. Can you share? Okay. All right, thank you. Can you share with us the sort of vetting process that NOAA or that you would go through in maybe sharing products and services, some of the things that you identified up there? What would you go through before you begin to make things more public?
It would depend on the product or service. If it were a tsunami model, that would have to go through the benchmarking process that John talked about. So if you have a new tsunami model that includes dispersive dynamic or some other thing that maybe isn't included, that would go through the NTHMP benchmarking process. And then once it's validated and vetted through that process, then the states and territories can use that model to generate hazard maps that are supported by the NTHMP. So that type of thing would go through the NTHMP benchmarking workshop. If it were a new way to interpret GNSS data for earthquake detection, or if you have a bottom pressure sensor that would be useful for tsunami detection that you think would be great to incorporate into the Tsunami Warning Center process, you would reach out to the Pacific Marine Environmental Lab and they would work with you to understand its readiness or their ability to implement it into the Tsunami Warning Center system. So I guess those are a couple of examples. So if you have a policy that you think should be implemented, you would reach out to either NOAA Congressional Affairs or to me, and we would then put that through, the NOAA process for implementing policy, or you could go to the Tsunami Science and Advisory Panel and make a recommendation to them for them to bring to us. So I would say those are the venues.
How about a loss model?
A loss model. NOAA doesn't really do loss modeling at this point. That would go through the NTHMP at this stage, but
I would say that you would actually, start with the state science and education outreach NTHMP representative to discuss those and see how that might actually fit into their respective programs. I think I indicated that all states, basically all the Western states have actually done some form of hazards type analysis of losses, casualties, etc. And so what we want to avoid, and I mean, don't get me wrong, hazards has got its own limitations and problems. And so there's a lot of work that still needs to be done, as we heard yesterday, in terms of improving the science there. But what we don't want to do is start putting out products that actually conflict with, say, what the state already has out there. So I would say start with working with the state NTHMP representatives, and then they can maybe guide you from there.
yeah, also FEMA, I would say reach out to FEMA. They do a lot of the loss estimation, and Kara's going to talk about that. She's raising her hand, but they are our go-to currently for hazards, and that's how we do loss estimation. And so they're the state or the federal agency that has more of a authority on that. Yeah, you have another question.
No, yes, say that. You were saying. Amy.
Thanks. I have a quick question about, after Tonga, is Adams going to include the flexibility for non-seismic tsunami messaging? How are we adding in sort of the research for landslides or volcanoes or other sources?
Yeah, great question. We would love to do that. And it is on our wish list, I would say. So right now, the CAS and the atoms are being developed to replicate the existing capabilities of the two tsunami warning centers with upgraded code, computing, and technology. But there's a document that we have that's essentially like, what can we do now? And then what do we need to do in the future? And so the hope is that there will be, you know, continued support for further development of CAS and atoms to better understand non-seismic sources, such as volcanoes and landslides, but that is not going into the current version of CAS or atoms.
Sorry, this was maybe already covered, but I was in contact with the PTWC recently, and I was surprised to learn that they did not have access to, let's say, medium scale computing and or HPC in general. Do you think this is something in the future which will change?
I hope so. Yeah, PML as part of the CAS development is working on getting them better GPUs, is looking into cloud computing. And all of that is very expensive, and especially with the uptick in cloud computing, you know, globally. And so it's challenging, and especially because both tsunami warning centers are in what's called a FISMA high system. There are very high security requirements, and it's difficult to build and to get the computing systems you need, especially cloud computing, in within those boundaries and requirements. But that PML is looking into that.
Karina, thank you for that presentation. I've been in the NOAA Sooniverse with you, and I, for one, am very grateful that you're in your role, because I know that you understand all the challenges and complexities that we face along this entire processing chain. One thing you talked about, which piqued my interest and is not a focus of this workshop, is early warning and rapid response. One of the things we've been working on with Ron and some of the other ImageCat folks is turning things like earthquake early warning messages into rapid tsunami forecasts, and then being able to provide rapid loss forecasts, like something like the pager product that the USGS puts out, that gives you a distribution of potential fatalities and potential economic losses. Do you see a future for that kind of product within NOAA or other kinds of response agencies, where we give you a very rough, quick look view of what you can expect over the coming 48 hours in terms when you think about how many losses there will be and what's the scale of the challenge that you're facing?
Yeah, I would say I love Pager for USGS. I go there and I really like the look of that website. I like the placards. I think it's really useful, quick information to be able to see that. As I said, you know, what's next and how, you know, what are the chances? I think that there could be interest in that. Tsunamis are difficult because we don't have, especially in the United States, a ton of data to validate that. And so I would say it would probably need to be well vetted and validated and proven before it could be included or adopted.
Yeah, on the side about, you know, how this then interfaces with the public and in the moment, and you and I talked about this last night, but I wanted to say this with the state folks as well. Is NOAA or the states talking to some of the commercial entities that provide information services to us all? And obviously what I'm thinking about is Google Maps, right? If you're in a tsunami inundation zone, do you have a thing that'll pop up on your phone and say, go this way? Which just seems like maybe it's a holy grail, but a goal that we should all have, because nobody's gonna pull out their evacuation map and start walking with their paper map. We don't use that for anything else, and we use, you know, we use our phones typically. So yeah, is that even in the horizon at all at this point, and can we make it so?
Yeah, I'll say just really quick, and I will pass to my state partners, that that would be great. I before I took this role, I have talked to some NOAA or some Google folks at conferences, and they're somewhat interested. And with the Google rolling out earthquake early warning, I also asked that at one of their conferences. There's challenges with that though, because in an event, we don't know what routes are open, operable, and if someone's, you know, like relying on Google to tell them how to get out, and then the road is blocked, and that wastes valuable seconds that you need to be going to high ground.
Yeah, but they know. right? Just like they give us
Well, they
real-time
don't-
traffic
I don't
information,
think it's that-
they'll have real-time information from the.
Not probably, maybe for a distant source event, but for a local event where the earthquake happens here, I don't know that they would have that in real time, and so I think it would be really cool, and I could work well in a distant source event, but for a local event, which roads are blocked and all that, it's really up to the people practicing and exercising and knowing where high ground is and having situational awareness to be like, I gotta get there, there's a huge landslide, I guess I'm gonna go this way. But I think what could be useful, that we were talking about, is like, when you come into Portland and it's like, Portland Transit has been added to your maps. It would be really neat to see, like, tsunami evacuation routes have been added to your maps when you enter a tsunami zone, so that it at least brings you awareness that you're in a tsunami zone and you could practice that in, quiet times. That would be cool. But I'll pass, John has.
So we have actually developed a product.
Oh, yeah.
That actually shows you routes for any location on the Oregon coast. And we collaborate with Washington DNR to include the Southwest Washington coast. So you can go to the NAOS tsunami evac portal. You can zoom in, you can enter an address, it'll tell you whether you're in the zone or not. It'll receive warnings from the tsunami warning center. You can click on anywhere in the inundation zone, we'll give you a route, it'll tell you how much time you've got to get to high ground, how fast you need to go. But it's all pre-disaster preparation. I mean, that's fundamentally what it's really directed towards. And so I think, as Karina indicated, during an event, cell phone towers are probably going to be down. And people aren't going to be able to pull stuff up on their phones in an event or immediately following an event, especially if it's cascading. So it's all really directed towards pre-disaster prep.
Thank you, Sarina.
Thanks, Karina. So I was kind of curious, on one of your slides, you said you are doing training and exercises, or that's part of your, mission. And I wanted to know sort of what level are you planning to incorporate in exercises? Is it the states? Is it other federal agencies? Is it actually getting to local communities? And if you could expand on that.
Yeah. So every year there are several different annual exercises. Yesterday actually was the land text exercise, which was an exercise for a large submarine landslide in the Gulf of Mexico. And so the tsunami warning centers asked people to register for this exercise. They reached out to local emergency managers, partners, the Coast Guard, the oil industry, people, that are interested, and then they sent out test messages and they could play along with what would they do. And it's an example for you to think about, what would you do if you got this tsunami message? And so there are similar exercises every year for the Pacific, for the Caribbean, for the Atlantic. And so the tsunami warning centers host those exercises annually. And then local entities and states also have their own exercises. And every year is part of the Great Shakeout. It's also, states and territories are encouraged to do a tsunami evacuation exercise as well. But then another exercise is just like within the tsunami warning centers, exercising backup capabilities amongst each other. But if you're interested in that, tsunami.gov is the place to find information about those exercises and how to sign up and participate. So please do that. Or the NTHMP has a resource called Sioux Info Alert. It's a bi-monthly bulletin. And if you sign up for that, it's a great way to get information about all the projects that the partners are doing. It's a place that you could anyone here could write an article for Sioux Info Alert and share new and emerging science with the NTHMP partners. That would be really great and welcome. And then they also post information about NTHMP meetings and exercises. Yeah.
We at the Hope University, where we have some research at the moment that's looking at some of the problems that we mentioned here about how to deal with facilities that, towers going down during a tsunami event. an earthquake and how to integrate mobile data modeling for anomaly detection in terms of routing to evacuation facilities during a disaster, so that we can do this kind of pseudo real time or with minimum delay estimation of whether some roads are going to be blocked, some facilities are going to be unavailable, and what the likelihood of this. And it's kind of like well, there's two different projects. One is a digital twin project that my supervisor is working on, and I'm not too privy on that. But on the more statistical side, we're trying to integrate agent-based modeling informed by model network communications, and how we can try to simulate dynamics that get as close as possible to the real traffic, pedestrian or traffic, so that we can kind of have an understanding of how routing works during a disaster and what's going to be clogged up and also. So I think that might be valuable down the track to you guys.
Yeah, absolutely. I think that could be valuable, and I think we'd have to collaborate with, like the Department of Transportation, because NOAA doesn't have access to those data or authority to see where people are in real time or use that for routing. And we are not the authority for evacuation routing. That is at the most local level. And so each city is in charge of their evacuations, issuing evacuations, and who evacuates to where. And so that doesn't come from the national level. I don't know if it's different in Japan.
No,
but,
no, it's exactly as you
yeah.
mentioned, and that's one of the issues we had, because, well, as you mentioned, you do have to work at the local scale, because all the routing happens, or maybe we're looking at a case study for Fragility, which is one of the closest cities to the Nankai fault. And so apparently it's, well, estimated tsunami time, arrival times are in the 20-minute margin. But yes, it obviously has to be local. And as you mentioned, we also don't have access to disaggregated individual cell phone data because of privacy issues, obviously. And so one of the challenges is trying to disaggregate the masked aggregated data that comes from the provider, and that's the level of detail that they are able to provide us on a commercial basis. And how can we implement that to create something that's tenable, that approaches reality? But yes, exactly. Those challenges that we've also been facing as well.
Yeah.
Okay, so this is the end of the question for this presentation. Thank you, Corina. But in a certain way, we are answering these kind of questions. So this is the general roundtable related with this session. Okay, so we have two questions here that you can start talking about this question or maybe others. So first of all, what are the major challenges to develop, I would say, a system, okay, the general system for general use? What are the major challenges? We have talked about this thing right now with the questions. And second, what are the major challenges to make results approachable to target users, industry agencies, and communities? So the session is open for any comment or question.
Okay, so I think this is actually one question for Jay, but before talking about that, I think it is relevant to these two questions. So that's the effective communications and collaborations between the scientists and the engineers and also between us and the communities. So the question, I'm also concerned about the logical tree width. He asked very good questions and you give reasonable explanations, but now the questions becomes should we just work closely with those experts to know the logics behind the selection of these values and how to reduce the bias as possible as we can. That because it might be very important. You spend a lot of times to collect the data and do the modelings, consider so many uncertainties into your probabilistic analysis based on which and you developed or propose a very smart way to get the representative scenarios, right? But with this if we use these representative scenarios to inform the design, either the new design or the build mitigation, for example, is for the mitigation. If it's bears, very bears, for example, we don't know. How can we guarantee this design are robust to the different so many uncertainties you are considering in the probabilistic analysis in the beginning? Yes, thank you.
Probably more question for you, Jay. So basically, it's the big problem of the weights in a logic tree. What do you think about that?
Say that again?
About the weights in the logic tree. So how we can, in a certain way, make sure that the quality of the weight in these logic trees are useful or not. Can you talk about logic trees?
Okay, so thank you for the question. And so how we solve, so I'll use an analogy for radiocarbon dating of paleoseismic events. So Gary Carver, Humboldt State was sort of a groundbreaker in paleoseismology, and he always said to only get one radiocarbon age for anything, because once you get 2 or 3, then they contradict. And then, in the ensuing decades, the approach is to get hundreds of radiocarbon ages, because then you have a distribution. So I apply this analogy to the subject matter expertise's estimates of weighting, and our method is to incorporate as many subject matter experts as possible, because then you get a distribution that hopefully represents the population. And so for each of our week-long workshops, we had between 30 and 40 subject matter experts that had a publication record on the subduction zone sources that we were considering. But of course, there's always a possibility, if not a probability. I don't want to know what the probability is, or maybe I do want to know, but I don't know, that we missed key subject matter experts. So that's always going to be the case. But we did make these polls available to people who were not at the meeting. And so that might be a way of improving this when we do it the next time, is to be better at inviting people who weren't at the meeting to provide their subject matter expertise. I hope that I'm going to pass this over to John.
So I think that's an excellent question, and I think this room here of all these experts highlights the ongoing process towards building out these updated logic trees. So right now a lot of the work that's being done here is not going to directly influence the existing PTHA update, which is scheduled for 2028, because that process is already well advanced. But it does feed into the next iteration, which is 2034. And presumably between now and then, we're going to learn an awful lot more. But I think on the positive side, maybe Diego can speak to this a little bit more, but I mean, for that one example, I showed the hazard curves from what was produced in 2016 and what's being produced now. There are fairly subtle shifts in the most critical areas relating to 24-75 year event scenarios. And if my understanding is correct, when you integrate across all these different branches and uncertainties, it doesn't change a lot. It tends to change at the lower ends of the tails, where you may be bringing in more smaller sources, and maybe not so much at the high end where you have fewer large events. But in the middle, things tend to converge and don't change a lot. Maybe Diego, you can speak to that a little more.
So, okay. Yeah, thank you for the question. Yes, so, so I think, that's good to know about the process. I think this is the improving process for the communications. You updated your logical tree models, and then when you learn more about your uncertainties or uncertainty reductions, especially for the epistemic uncertainties, and based on increased knowledge, and then you feed back to the expert, or even they have more knowledge about their field, and then they can update their ways, and then you work more closely to update the model. Yes, thank you.
I have questions about the major challenges. Is there a possibility that these logic trees is getting just too complicated? And there's the generation, obviously that's essential, propagation, and the inundation phase. The inundation itself has lots of uncertainties, how to deal with the built environment, all the levees and things like that in California. So is there a possibility that we're doing the best available science, which is good, but it's gonna just make it harder to get this product out in a timely manner and incorporate uncertainties for the inundation phase? So I guess that's just kind of a question.
I don't have an answer, but I have a question that is very, was my question is very similar to yours, and for Jay and John, and it's, I'm glad the logic tree is as complicated as it is, but now what you can do is you can actually see what branches are actually contributing to the hazard. And I wonder if there's been an effort to see like, oh, that branch, you can take it out and nobody cares. And so we can find branches that maybe we can lop off, and then we can focus only on the ones that matter, and then we can model, we have to run fewer inundation models, and then we can add those kinds of complexities.
Yeah. Oh, we'll leave another, maybe I can respond to that. The Cascadia logic tree is the most complicated of all the logic trees that are part of the AC PTHA process, because we know lots about Cascadia. So don't be disillusioned that the other logic trees are quite as complicated. In fact, like for the Pacific Sources workshop, we barely got to, how to segment the subduction zones and whether or not we, how persistent those second barriers are. So in terms of whether or not we can remove branches, it's important that we keep all the branches that we considered, but maybe keep a low weight on those to communicate to society and academia and everyone that those things were considered in the process. And so maybe we end up putting a zero weight on some branches, but it's important that we have at least that's the opinion of some people, is it's important that we have those branches. So kind of those are just some thoughts.
So, I'm moderator, so I can maybe later can ask the questions.
So I sort of have a question maybe for some engineers in the room, and it's kind of an implementation question from the Powell Center work with this huge PTHA effort. So one of the projects is going to be tons of different, return periods for these different hazard level curves and things like that. At the state level, we're going to be prioritizing a 24-75 year event for the AC building code updates and things like that, which is going to take a lot of time and effort given the capacity that we have in terms of, the modeling, people that we have in our office and I'm sure other states are probably feeling this pressure too to get that work done. But after that, return period, it gets modeled for our state. I'm kind of wondering what other return period is a priority, in terms of, implementing for different, building like codes and like different industries and things like that. Like, I know in the pre-assessment workshop, I think on the first, yesterday, in the beginning of the day, it was the two extremes that were the, that seemed to be most prioritized, that 100-year event and that 2,500-year event. But I was kind of wondering if people could comment on that, and, is there also importance of, let's say, the 1,000-year event to model for maybe like bridge seismic retrofits and things like that? I guess if we were to prioritize another return period modeling at the state level, what would that be? Because there's not a lot of time and it's gonna take it's a lot of effort to do these, hazard assessments and things like that.
And actually, I want to give the microphone to Dan maybe, because yesterday I saw one of the results, I think was your presentation about what was happening in 100 with a tsunami. And it was like, who cares? Really, the things in the very high return period. Maybe you can.
Yeah, I think one thing though, this was the results on land, and there's a lot of, things that are directly on the water, like ports, fisheries, that kind of stuff. So I think this is just one small example. But yeah, I think somewhere between these two extremes, I think is, I don't know if you want to call it like most probable or something like that, or worst risk scenario. Because ultimately it does come down to scenario planning, and if you show people worst case all the time, they don't want to plan. If you just show them a far field event, there's nothing really to plan for. So I think there is something, and it has less to do with building codes and a little bit more with like what would be worst risk scenario to plan around, just to get people accepting the idea of doing something. I guess that would be my. So it's less about regulations, a little bit more just getting people to plan around that. Higher risk.
I would like to follow up on Dan's question about the major challenges, and probably this is a question for Paulina and the others. This is great. I mean, this is a modeling level we are doing, and it's fantastic and super complex, and all these logics are amazing for scientists. But when we tell the people what's going on, I think we made a mistake. And the example is the Tonga tsunami. It was a tsunami, and in Oregon, there was a warning of between 1 and 3 foot high tsunami. I have never seen more people on the beach waiting for the tsunami. It was crazy. And yes, of course, people are surfing 6 or 8 foot waves, and people don't understand what is the meaning of the height in comparison to the horizontal velocities of the tsunami. That information is not given to the public, and we are miserably missing that point. So we have amazing maps of how far the tsunami is going, and like, that is not what is gonna kill you. Is this motion the one that's gonna kill you? So I think that's a challenge to me, that I have so much hard time in the lab explaining to people that the tsunami is not what they see in the movies. It is not a tsunami like the rock is going into the San Andreas movie. I don't know if you have seen that. It's so bad. Anyway, so that is a challenge. We are missing the point to the public, and we're talking about the general public. 99.9% of the public are not understanding our models, but they see the movie.
Yeah, I agree. I think, communicating the hazard is a challenge, especially with Tonga was extra challenging because of the limited observational data we had to provide that forecast. And the warning centers did a great job with the limited information they had for that event. But there's not a lot, even in the best case scenario where you have tons of observational data, it's a distant source event, you have time, it's challenging to communicate like, yeah, what is a 3-foot tsunami? What does that look like? What does that mean? And that's where I think those graphical products come into play. That's where the emergency managers come into play to close the beaches and make informed decisions based on that data. But sharing that with the public is very challenging, and I think that's where social science comes in as well, trying to understand how do people perceive the hazard, how do they use that information for decision making, and then are there different terms that we could be using to communicate the hazard that would be more meaningful to people? What does that mean? And then providing that information for what actions you should take in alerts, and how do we graphically or communicate that? And I think almost no matter what, there will be people, unfortunately, that go to the beach, which is not what we want. And it's human nature to be curious, and so there's this battle of trying to provide information and inform decision making, but in a fire, people refuse to evacuate their home, even if they see the fire, you know? And so it's just a challenge. Yeah, that we have to go through.
Oh, sorry, I was just.
Oh, just coming back to the issue of the timelines, I'm a policy person, so this is like the kind of thing I think a lot about. I feel like there's, if we think about how we plan for land use and infrastructure, at least in where I'm at, it totally makes sense to think about a 100-year event. In that we do 100-year, the 100-year event is totally how we plan for flood, and there's a lot of land use regulation and building codes that are arranged around the 100-year event. And also for some bigger, more longer term projects, or like zoning where we're like a new part of the city that's coming in, we would look at a 500-year flood event and plan around that. And for a big piece of infrastructure, like a bridge that we want to last a long time, that might have a 100-year life, we would look at a 1,000-year event, because that's like a 10% chance in the lifetime of the object. So I feel like that 100, 500,000, it's embedded in our way of thinking in a lot of other places, and it also makes it kind of an easier sell, because it's like, well, we regulate on the 100-year floodplain, why would we not regulate on the 100-year event for flood, or we plan on the 5,000-year event in these other instances? So that analogy, I think, makes it compelling to policymakers.
Exactly that.
No, one more thing.
Over here?
Over here. It's coffee time. Okay, maybe one else, and then we go to baby.
On this side of the.
I just had a question out, so, and we talk a lot about recurrence intervals and planning for buildings, but in real time, how is all of this information going to be used when what we have is a magnitude, a location, a depth, and then a warning basis for that information? Is there a way to incorporate in, the evacuation space on the 500 or the 100, but then how do we link that to that magnitude of that event? Very open question, I don't know.
It's not right now.
Who would like to answer the question?
Zab, around. Did you raise your hand and answer?
I feel, oh.
In my mind, and please others jump in and say that you disagree with me, in my mind, the probabilistic modeling, the PTHA, is for decision-making before the event. It's for planning, it's for evacuation purposes. What is the worst case scenario that we want to plan for, so that we can design evacuation routes for that, so that we can build vertical evacuation structures to withstand that event, so that we can design bridges to withstand X level of event based on the building codes. That's where the PTHA mapping really comes in, is for before the event, understanding what's probable and designing and planning for that. But you're right, in the event, we don't know if it's a 2,500-year event. We just have a magnitude and a location and a depth. And so the Tsunami Warning Centers issue an alert based on that in the historic database. And then as we get DART observations, then they can update their forecast based on that. And so that's why I think a lot of emergency managers like to understand what is the worst case scenario for my community, so that I can plan for that for evacuation. And then understanding what is a distant source event, so that if I see an earthquake in Alaska, maybe I don't have to evacuate people as far, and understanding that. But I don't think the PTHA really goes into real-time decision-making. It's more for preparedness and planning. I think there is space for probabilistic forecasting, which would be like ensemble modeling and trying to understand the event and better earthquake or source detection. But to me, those are different probability models and things. One more.
And then we go to the coffee, otherwise we will miss the coffee.
So the way I approach it is, what can I get, Aunt Martha, who is an 80-year-old woman on the coast, to understand? And if she hears 2,500-year return, well, I don't have to worry about that. But it's much easier for me to sell to the public 100, 500-year return intervals. So, Corinne said, it's for policy making, that kind of thing. But when I'm trying to translate all of this to public messaging, I really, really, really have to simplify it down and make it something that is touchable and approachable to them. It makes it relevant. 2,500 years,
Doesn't make.
yeah.
Actually, that is slide I showed yesterday about the comparison with the lifetime.
Yeah.
It's basically trying to address that is specific from that everybody see remotely.
I have a response.
So, yeah, and this is the last one.
The last one.
Then we go to the coffee.
So after 2010 and 2011 in California, emergency manager that were not a maximum credible tsunami, emergency managers in California wanted some way of evacuating less than the entire area and the evacuation area. And so what we developed, based on the forecast amplitudes from the NTWC, is that we developed with the National Weather Service an acronym called FASTER. And it's basically a program that we developed where we take those forecast amplitudes, we combine the sea state, the tides, and 30% uncertainty, and then export a recommended evacuation level. And so we've developed these tsunami playbooks that are phased levels of evacuation. So the lowest phase is the minimum evacuation, and then maximum phase is the entire evacuation area. And so then we provide these to the counties. We have an hourly call during an event, and we provide these recommendations to the counties so that the first responders and emergency managers can accept our recommendation if they like and evacuate a small area. So that's sort of an approach at, taking the forecast amplitudes and then, helping the emergency managers make a better decision. It's not exactly what you were suggesting, but.
Thank you. Okay, so now we will have more time in the round table. I will keep my question for the road, let's use about those last questions as another. Okay, let's go for the coffee.